Colonoscopy is a procedure that utilizes an endoscope for probing and diagnosis of gastrointestinal tract diseases, primarily in the colon. The colon is susceptible to diseases like colon cancer. Since the region is hard to reach and images from conventional imaging modalities is not as reliable or accurate, an endoscope is being used due to its far-reaching capacities as well as its flexibility. An endoscope is a device that consists of a long tube that is inserted into the body. The tube consists of a camera and may include other surgical devices. In conventional endoscopy procedures, doctors guide the endoscope based on the images being fed from the endoscope camera. Due to this, they rely heavily on their skill and judgment in moving the endoscope inside the body, since they do not know the exact location and spatial configuration of the endoscope. However, the doctor may encounter problems when the endoscope gets tangled up, and this causes excruciating pain for the patient, and it is difficult to untangle the endoscope without knowing its spatial configuration, as well as due to the boundary conditions in the human body and is very narrow. The tangling of the endoscope must be avoided in the first place. The problem can be solved if a localization method is employed. That means that several reference points are attached to the different segments of the endoscope, and each of these reference point position and orientation is determined by using sensors. The number of sensors used is based on how many points you place on the endoscope. Based on this information, the doctor can accurately know the spatial configuration of the endoscope. In magnetic localization, the sensors used employ electromagnetic fields that detect the location via their magnetic field intensity. The basic components of the system is illustrated in the diagram, where there are emitters on the endoscope itself that transmit electromagnetic waves. The control unit controls the emitter drive electronics to generate an exciting sine signal to the drive emitter in the endoscope, which then generates electromagnetic waves in space. There are 9 coils of the 3 receivers with given positions that produce electrical signals with certain amplitude and phase in response to the sine electromagnetic waves. Under the control of the control unit, all together or in sequence, these signals are amplified and filtered in the measurement unit and dealt with from analog to digital conversion, and as well as fast Fourier transformation process in the data process unit. The data with useful information will be used in a certain algorithm for localization in control and unit, and the position of the emitter will be calculated. Then the curve of the endoscope, which represents the position of every emitter in the endoscope, can be obtained by fitting a curve to the certain points. Finally, the fitted curve will be displayed in a display unit. The fundamental principle of electromagnetic method for localization is that electromagnetic signal caused by driving electrical coils with sine signals has a specific spatial feature. The receiver with 3 axes of coils that are pointed to the x-axis, y-axis, and z-axis respectively is located at the origin. Emitter P is a coil with axis pointed to vector S. R is the distance between the receiver and the emitter. As the voltage induced in the receiver is only related with the position and the orientation of the emitter, then formulas with induced voltage and position of the emitter x, y, z, the inclination angle theta and rotation angle phi can be conformed. Both generators and sensor coils are small enough to be good approximations to theoretical magnetic dipoles, so the magnetic dipole model is used in the equations between sense, signal, and sensor information. The magnetic intensity at P can be calculated using the magnetic dipole equation, which is B equals to mu naught over 4 pi r cubed times 3 m dot r times r over r squared minus m, where mu naught is the magnetic permittivity, m is the magnetic moment of the magnetic dipole, r is the vector from the magnetic dipole to monitoring point, and r is the magnitude of r. An object needs 6 parameters: x, y, z, m, and and P to accurately describe its position and orientation. The M, N, and P are direction information, but there exists a constraint for the orientation such that m squared plus n squared plus p squared must equal to 1. Therefore, there are actually 5 parameters. The magnetic intensity sensed by the coils can be represented as B equals to the x component of B times m, the y component of B times n, and the z component of B times p. And from that equation, you can derive the different equations of the different components of B by the following equations. Using these equations, you assume that B of B subscript T is a constant related to the air magnetic permeability, whereas M subscript S, N subscript S, P subscript S is the direction of M. And XYZ is the position of the sensor, ABC is the position of the exciting source, and R is the distance between the source and the sensor. For each exciting source, the magnetic intensity sensed by each of the sensors within the colonoscope is measured, and for N sensors, N measured values are gathered. 5 sources are the minimum to solve because there are 5 unknown position and orientation parameters, which was X, Y, Z, M, N, and P. But as the equation is nonlinear, analytic results are not achievable, so we can only get an optimum solution through numerical methods. Therefore, the more equations there are, the better the result is. The magnetic field components X, Y, and Z, which was described earlier for each point on the endoscope, is then detected by the sensors, and from the equations the positions is used to solved numerically and is used in curve fitting. Once you acquire the positions of each point, you can construct 2 unit vectors, U1 and U2, for the 2 points P1 and P2, joined by a length of endoscope of length L. P1 and P2 is basically the different positions of 2 sensors on the endoscope. Curve fitting involves finding a quadratic equation of F that describes the spatial configuration of the length of endoscope L and is a function of time. F is assumed to be a convex function. The curve F is found by looking at the changes of U1 and U2 with respect to time, and is described by the following equations. For each position component of each point, the derivative of F with respect to time is calculated. Then by finite difference method, F is computed numerically. This can be done in MATLAB or OpenEMS by discretizing the time intervals into small sections, as well as further discretizing the whole length of the endoscope into smaller intervals. The method of forward or central difference or backward difference can be used. The final plot of F can then be displayed as a 3D curve. This can be done because for each value of F calculated in the finite difference method, it yields a vector of F, which can then be plotted as a 3D curve. This 3D curve can then be superimposed into the boundary of a human intestine or a colon. For our project, we will start off with the simplest case where there is only one point on the endoscope, and if time and resources permits, add complexities like boundaries, as well as trying different curve fitting algorithms that might be a lot better to the model in future ventures. Finally, the end product of the end of adding multiple complexities should look somewhat like what these students did in this snippet. All in all, magnetic localization is the combination of utilizing electromagnetic concepts and curve fitting techniques to solve real-world problems in the medical field. Further research in this field is required to ensure better quality medical services and patient well-being.